Okay, so I'm going to be taking the information in this first problem and creating the area model that they ask for. So when I come over here for my area model, just to get us started, I have spinner 1 and spinner 2. I think, I'm just going to do this. So I've got spinner 1 and spinner 2 right here. Let's do this a little bit. So I know that on one side, there we go, nice and big. Let's go spinner 1 on the top. So spinner 1 is on the top, and I have 3 possible outcomes. I'm not trying to draw the proportions correctly because I'm not that good. So I'm just going to draw 3 equally spaced columns. I could get an I, a U, or an A. And then for spinner 2, get this in here, spinner 2, I can have true or false. As we're looking at this area model, spinner 2 probably is the one that's easiest to understand. True has a 1/4 chance, and false has a 3/4 chance. Now when it comes to spinner 1, it's a little bit trickier, but all we have to recall is that a circle is 360 degrees, which means U is going to be 60 over 360, or 1/6. Now here's the part where I want you to be careful. I mentioned keeping the denominators the same. At first, it's easy to recognize that I is 1/2. But if I make I over here 1/2 and my denominators aren't the same, now it's going to be harder to compare my boxes inside. So instead of writing 1/2 right here, I'm instead going to write it as 3 over 6. This way, because I have the same denominator, it's going to make it easier to compare the boxes inside of my area model. Finally, keeping by the same detail, if 3/6 is for I and 1/6 is for U, that means 2/6 must be for A. 3 plus 1 plus 2 is 6, therefore I have 1 whole spinner accounted for. Just like before, I can multiply the boxes to fill the space inside. So I have 3 over 24, 1 over 24, 2 over 24, 9 over 24, 3 over 24, and 6 over 24. And the reason I like this area model right now is because since all my fractions are over 24, it's really easy to see which ones are more likely than the others. Obviously, this box right here is more likely than this one. It's easy to compare those fractions. Now, in order to complete this problem, I also need to have an understanding of the sample space. So I'm going to put the letter combinations down below as well. So I can roll an I and a T. I can roll a U, T. I can roll an A, T. I can roll an IF. I can roll a UF. And I can roll an AF. Those marks in red are my sample space. Those are the possible outcomes. So IT is an outcome. AT is an outcome. They may not be equally likely, but those are my outcomes. If I asked you for the sample space of this problem, you would tell me these 6 two-letter combinations. Now, when we get back to part B, they ask us to calculate the probability that you will win this game. So when I come over here, we are going to use this table to find the probability of winning. Now, in order to understand what it means to win, we need to go back to the problem, and it says that you win if it forms a 2-letter English word. So that means out of these categories, which ones are English words? And specifically, they are going to be IT, AT, and IF. So based off of those 3, I can take their probabilities. IT has a probability of 3 over 24. AT has a probability of 2 over 24, and IF has a probability of 9 over 24. Now, based on those, if I want to get the total probability of winning, all I have to do is add these up. Adding those up, 3, 6, 9, 15 over 24, which if you simplify is going to give you 5/8 or 0.6, I want to say 625, but I'm not 100% sure on that because I can't remember my eights. 1.25 times 5 would be 625. Cool. Okay, so 5/8 or 0.625. Either of those would be acceptable answers. Finally, in part C, it asks, is this game fair? If you played the game 100 times, who do you expect to win more often, you or the teacher? Can you be sure this will happen? So if you haven't already, take a moment and consider that question right now. Is the game fair? Over the course of 100 plays, who do you expect to win more often and why? If you haven't already, pause this video and take a moment to consider that. Okay, so here's the key detail. A game is fair. This is the math definition. You probably like this game because you have a bigger chance of winning, and winning is fun. But in Mathland, a game is fair if no party has an advantage. That is to say, both sides are equally likely of winning. Where this changes a little bit, and we'll get into this in a section or two, but there's an idea called expected value. And what expected value does is it takes into account how much you pay and how much the prize is when you win. So for example, something like the lottery, you don't pay very much and you're very unlikely to win, but the prize is really, really big. So it kind of accounts for all of those factors to really decide if a game is fair. That is to say, if you play it long enough, will the money you put in be the money you get out? And we'll explore that later on. For right now, when we look at this situation, clearly the person who's the student trying to get the 2-letter word is more likely to win. So in that sense, this game is not fair. Had we found this probability right here and gotten 4 over 8 and 400 and 500 right here, then the game would be fair. But as it stands right now, this game is not fair.